from these models here, very few meet these two conditions, being open and being ready for Catalan. So, well, to close this gap and develop such models for Catalan, we can ask ourselves what was needed to train those very successful models like this one here. We were interested in the parameter size of around 1.3 billion, which we consider to be a first starting point in our research. And here we can see the number of tokens used to train, for instance, GPT-Neo, 240 billion tokens, 180 billion for OPT, and the smallest number, as you can see, is 26 billion tokens, which is consistent to Chinchilla's scaling laws that can be interpreted as the compute optimal amount of data to train models from this size.
However, when we started our research a few months ago, we were some way off. Despite our best efforts, we only managed to compile a 5.3 billion token dataset in Catalan. So given these constraints, the question is also these constraints are inherent to any mid-resource language. So how can we train a competitive Catalan model? What options do we have? So we'll focus on the available training strategies.
Yeah, the first option, the most standard one maybe, is to train a model from scratch. Although, of course, many research is currently being done in this line, it fundamentally consists in training first a tokenizer for the target language, and then randomly initializing all the model weights, the embedding layer and the transformer layers. And of course, then the weights are optimized for that language through training. This option has been widely used for many languages, for instance, for Spanish, for Chinese, for French, among many other languages.
Yet, an alternative approach would be to do language adaptations that we deem more suitable for our situation. But this means to reuse an already existing checkpoint. So, but what exactly does this mean? Let's assume that we have a model that has been already optimized for a particular language, such as English, the most common one, and has learned to predict the next token over a vocabulary, given the previous context. So in other words, it meaningfully processes an English context, taking into account the nuances of that specific language, to produce a distribution of the probabilities of the next token over a vocabulary. What we really want is to shift this distribution from English to our target language.
Within language adaptation, the most straightforward option is to just continue the source model's pre-training with the new data in the target language. This means to copy the transformer layer weights, the embedding weights, and of course also the vocabulary and tokenizer, and just start the training from there with the new data. In the literature, there are a few examples of this technique. For instance, GPT-J, an English model, has been adapted to French like this, and Llama has been adapted to Portuguese like this.
In this method, we are reusing a vocabulary and a tokenizer prepared for another language, and it may not be entirely suited for our target language. Moreover, keeping the source language tokenizer will lead to a more ineffective tokenization and will probably break down more tokens. And if you ask how this is relevant.
Yeah, the answer is that more tokens means that we will need more tokens to represent the text. And then we will need also more time to process these tokens. And also the context window from the model will be filled earlier. Also, some research like, for instance, Arteche et al. Seems to suggest that language-specific tokenization is related to a better downstream task performance.
a language-specific tokenization is exactly the focus of this work, and there's a lot of approaches that seems to propose this. But what we really want is to modify the tokenizer and to modify the vocabulary. So what we can do is to reuse the transformer layers, but we cannot reuse the embedding layers. So the exact steps to do vocabulary adaptation, in our case at least, the ones that we have tried, are to train a new tokenizer, the same that we'll do to train a model from scratch. Here there's a lot of things to say about fertility, etc., but we'll leave it for another talk. And this provides us with a tokenizer and a vocabulary in our target language.
Yeah, but now the problem is that the new tokens do not match the old embeddings from the source model. A naive approach would be to just reinitialize the embedding layer, discard the English one, and just reuse the transformer layer weights. But the literature gives us better options, and the one that we chose for this work is the following. Given a source vocabulary, in English in this case, and the target vocabulary, there are some tokens that appear in both of them that we call the matching tokens, and there are some other tokens that appear either in one or the other vocabulary, the non-matching tokens. What we did is to copy the embeddings corresponding to the matching tokens from the source model to initialize the embeddings from these tokens. And the embeddings from the non-matching tokens were initialized as the average of all the source embedding weights.
This allows us to leverage the embeddings of the matching tokens, but what happens with the other ones, the non-matching ones? We have just these average that have never been trained. Is there something that we can do to train them before the training of the full model, or we must just start the full training?
We looked at 3 alternatives here. Yeah. The first was, as he mentioned, to directly train the full model weights with the new data. The second was to freeze the transformer layers and to train just the embedding layer. And the third option was to freeze the whole model and then gradually unfreeze it layer by layer as a kind of warm-up. We tried these 3 options with a small subset. We compared the evaluation loss results with what you see there. And interestingly enough, the best option was to directly train the whole model weights. And this was the option that we chose for our later experiments.
Now, let's dive into our training data. As we said, our goal was to train a competitive Catalan model of around 1 billion tokens, and that we only had 5 billion token datasets, which significantly lags behind what chinchilla scaling laws would recommend. One could think that a possible solution would be to do 5 epochs on our data, but there's this paper from Morning of et al. That says that we can only do 4 epochs of our data without harming the performance of a model. So what we did was to do oversample the high quality datasets. Here we can see all our sources, but trying to not overpass the 4 epochs for each. And also what we also did was to go for the closest language that we could, that it's Spanish, and take some datasets as well from that. We also include a little bit of English data because we were trying to maintain the original capabilities of the models before language adaptation. This makes our models multilingual.
To evaluate the strategies, we created a new evaluation benchmark with what we saw that is a necessary effort for many mid-resource languages. We designed this benchmark to cover several evaluation areas. Here we have reading comprehension, question answering, natural language inference, paraphrase identification, common sense reasoning, and translation. Our priority was to evaluate in Catalan, but we were, of course, also interested in Spanish and English. And therefore, we have included the 4 data sets that are marked in blue that were directly designed in Catalan. But we also included some multilingual data sets that were available in the 3 languages, or at least in 2 of them. Also, we used Illuthor.ai's evaluation harness as a framework for evaluation, and we evaluated in a 5-shot setting only.
Finally, we got to the experiments where we tried to compare the from scratch strategy. So we train a model from scratch with the continual pre-train strategy that we just explained without changing the tokenizer, and with the vocabulary strategy that we change the tokenizer. In both cases, in the CPT and vocab adapted models, we continue from the Cerebra's original 1.3 checkpoint. This is because it's one of the few models that comply with the chinchilla scaling laws, and we were interested on that. So what can we conclude from all these results?
First, the 2 language adaptation strategies performed better than training from scratch. So this shows us the importance of the initialization strategy, and more specifically that the weights optimized for one language could be successfully adjusted to a new language through a language-specific training, and that this was preferable to just starting the weights randomly.
When we compare both vocabulary continual pre-training strategies, the CPT and the vocabulary adaptation one, the first thing that we must notice is that they do not share the same tokenizer. So the CPT model, they both were trained on the same amount of data. So the CPT1 has been trained on 38 billion tokens instead of 26 as the other one. So it's much slower, and it has obvious downsides. However, what's more important is that it seems that when we adapt the vocabulary to our target language, it outperforms in most of the tasks to the CPT1. There's an exception maybe with POSEX, but it's very close to random, so we don't feel like it's relevant. And also, if we take a look into the English tasks, it's interesting because both models, of course, all this strategy lag behind the Cerebra's one because we are changing from English to the other one, and it seems that well, we are forgetting most of our English data. But it's interesting to notice that even in that scenario, vocabulary adapted models seems to outperform the CPT ones. We think that more research it's needed at this point.
Yeah, and finally, as we already mentioned, we noticed that the 2 language adapted models are behind the original, the source model on most of the, or in all the English tasks, which is quite reasonable given the Catalan and Spanish specific training. But at the same time, this arises some questions like how to better maintain the English capabilities, if this can be improved through changing the proportion of English in the training data, and whether this keeping some English data in the training data set can be also benefiting the 3 languages by creating some kind of anchoring effect, which we also saw in literature.
Now we more or less know that vocabulary adaptation seems the best strategy, but it's quite clear that English it's not the closest language to Catalan. So departing from English, it's not only that the model has only English knowledge, but it's also that the amount of matching tokens, so reusing the reused embeddings, are much less than if we could start from other places. So that's the question. Could there be a better starting point?
And at this point, Bloom models seemed good candidates. They are open, and there are Bloom models available for the parameter size that we were interested in, 1.3 billion. Specifically, there is a 1.1 billion and a 1.7 billion Bloom models. And also, well, their training corpora includes some very closely related languages and even some Catalan.
So we perform vocabulary adaptation over both Bloom models, and here we have the results. We compared our models with all the previous experiments, the ones that we already explained, but also with several baselines. We took as much models of around 1 billion tokens that we could think of. So we have the multilingual GPT and the original Bloom, but also several monolingual baselines, Pythia, OPT, Falcon, Cerebras, and also GPT-Neo. So here we can see the results obtained in reading comprehension and question answering. It seems quite clear that in Catalan and in Spanish, the Bloom's model seem to perform in all tasks and languages. If we go to the natural language inference and paraphrase identification, it's again the same except for POSIX, where the results are quite close to random and they do not seem to manage to do it quite well. If we take the results of common sense reasoning and translation, what we see is that we also seem to perform well on those, but translation seems the best one. Bloom models perform amazingly well in translation tasks.
If we try to think about what's behind Bloom's improvements, we can think at least of these points here. First, as we said, its training corpora includes some Catalan and some closely related languages, but also its training corpora is huge, which could be an important factor also.
Yes, and another probably key factor could be that there is a higher token overlap between the Bloom's vocabulary and our target vocabulary. It's actually about 66% of our Catalan vocabulary. The reason behind this is because Bloom's vocabulary is huge and our target vocabulary is not, so a higher token overlap may result from that.
Mm-hmm. Also, it's important to mention that vocabulary adapting Bloom meant to reduce the 250K vocabulary size to 50K in our Catalan vocabulary. And this, adjusting correspondingly the embedding layer, its size, and then it implies an important model compression. So we downscaled the original 1.1 billion Bloom to 760 million parameter, and from 1.7 to 1.3 billion.
We've been collecting some unresolved questions along this presentation. Let's try to recap some of them. The first one is how to improve vocabulary adaptation, technique. Especially when it comes to the non-matching tokens. We've seen that we took like a naive approach. Could be there a better way to create a suitable lexical embedding for our new vocabulary? That's the question.
Also, we mentioned that the English capabilities were harmed during the language adaptation process. And we ask if this is absolutely necessary or if there's some way to avoid it. And also what are exactly the capabilities that we are losing, if it's only language-related knowledge, or if it's also common sense and word knowledge and other translinguistic capabilities.
Also, the question about how much training do a model need when you are adapting from an already pre-trained checkpoint. Do chinchilla laws still apply? We assume that, and we took that as a reference, but if we have a checkpoint like Bloom that has been trained for 300 billion tokens, do we still need the chinchilla laws to perform well, or it's still compute optimal to do that if we follow the chinchilla scaling laws reason?
Another question, how does the choice of the source language affect the language adaptation? Is starting from a multilingual model always better, deductively going from linguistically general to language specific, or it is sometimes better maybe to go from a specific language to a different one?
Finally, let's recap our main takeaways to finish. Please do not train from scratch if possible. Do it only if you cannot reuse an already existing model.
Better adapt the vocabulary to your language instead of just continually pre-training the model. And finally, use the model pre-trained in a closed language as a source model. And if it has seen the target language, then that's even better.
That was all for now. We would like to thank Cerebras for this workshop and also Yishi's team for his support throughout this process.
And that's it. Thank you very much to everyone for your attention. And if you have questions, we are glad to discuss them now or at any time.